Okay, but it will have to do, so you can see my slides now, right?
Yes, it's working pretty well.
Okay, the only thing is I think you will see two slides at the time. I don't know why, but we'll have to do it like that. So good afternoon or good morning.
Okay, let me introduce you, please.
Okay, all right. I was ready to start.
All right, thank you. And so Professor Marie-Amélie Boucher, she is an associate professor at the Université de Sherbrooke in Quebec, Canada. She is currently a long-term visitor at the European Center for Medium-Range Weather Forecast. Professor Boucher is one of the co-chairs of HAPEX, the Hydrologic Ensemble Prediction Experiment, a global community that brings researchers and practitioners together to advance topics related to hydrological ensemble prediction. Her main research interests include data assimilation, pre- and post-processing, forecast communication, and socioeconomic value of hydrological ensemble forecast. Thank you a lot for your accept of our invitation here, and please go ahead with your presentation. Thank you a lot.
All right. Well, thank you for inviting me. It's a pleasure to be here. So I will talk about data assimilation in hydrology by neural networks. And the planning of this course did not exactly go as I was hoping for it to go, in the sense that I wanted for it to be not too conferencey and a little bit active. And unfortunately, it will not be that active, and it will probably be, unfortunately, a little bit more on the conference style side, because as I will explain a little bit, this whole project was initially developed in MATLAB a while ago, and then I haven't touched on that for a long period, a couple of years, and I only recently got back to it, and I'm trying to improve the initial framework. And the first thing that we did is to translate everything from MATLAB to Python, but this is still ongoing. So I was hoping to be able to at least do a sort of demonstration using the new codes in Python, but unfortunately this won't be possible, so there will be no demonstration. It will be just explaining the general idea. But please, if you have any question, feel free to interrupt me during the talk. It will be my pleasure to answer. So just first, I wanted to talk a little bit about Sherbrooke. As Haroldo mentioned, I'm normally at the Université de Sherbrooke, which is in Quebec, Canada. There is a little arrow here. I hope you can see the mouse. Can you see the mouse? Yes? Okay. So it's a small town in the southern portion of Quebec, and there is a university there. That's where I normally work. And as Haroldo also told you at the beginning, I'm temporarily at ECMWF in Reading in the UK because I'm on sabbatical from the university. And one of the projects that I'm working on during my sabbatical is this data assimilation using neural networks. So I'm trying to continue to improve the framework that I proposed in 2020. So machine learning and streamflow forecasting, they have been linked for a long time. So in terms of research, machine learning techniques have been applied to solve different hydrology-related problems for more than 25 years easily. So the basic idea that we still often see is not really, it's nothing related to data assimilation. It's just using a machine learning model, for instance, a multi-layer perceptron, sometimes with one layer, like what you see here in this kind of scheme. And we provide this neural network with different hydroclimatic data, for instance, stream flow, precipitation, like the previous stream flow, a few previous time steps of precipitation, perhaps temperature. And then the output that we are looking for is the forecasted, a short-term stream flow forecast. So that's very traditional, if you want, and it's a very common application of machine learning technique in hydrology. So I did that for a while and then stopped doing that. And later on, during a conversation with a colleague from McGill, decided that maybe there would be other potential uses for machine learning in hydrology. And one of those uses could be data assimilation. So here is just some equations, for instance, the equations of the functions, the transfer function in the neurons. I'm not going to go through that. So basically what I just explained is this here. So we wanted to see if maybe machine learning techniques could be used not as a replacement for more traditional hydrological models like physics-based model or conceptual-based hydrological models, but more in support of hydrological models in the whole forecasting chain. Because when you want to produce stream flow forecasts or hydrological forecasts in general, it's not just the model. You need much more than the model. So you need to pre-process your meteorological data. In terms of meteorological data, you need both observations and also meteorological forecasts. And you need to do data assimilation. So data assimilation is a component of a forecasting chain. It's what you do at time t0, so just right before producing a forecast. So the basic idea to start with was to try to improve portions of the forecasting chain that are strictly mathematical. So data assimilation is one, pre and post processing of ensemble forecasts and bias corrections could be other ideas. And I know that now there are quite a few researchers working on that. So I saw some recent papers about using machine learning for post processing and pre-processing ensemble forecasts. So, but we wanted to go towards data assimilation. And in order to keep things relatively simple, I decided to go for a very simple hydrological model, possibly the simplest one that exists. I'm not sure of that, but it's a pretty simple model. You might know this one. It's the GR4J model. It's developed in France, and it has 4 parameters. It's a daily time step model. It's conceptual. It's also lumped. So it's very simple. You have a scheme of the model here, and you can see that it has 2 reservoirs. So one is it's called the production reservoir, and the other one is called the routing reservoir. So the first reservoir, it's basically your soil. So it's the storage of water in the soil layer. But it's very conceptual. It's a pool, basically. And when it's full, it's overflow. And one of the state variables of GR4J is the total capacity, not the total capacity, the water level at any given time step in that reservoir. So that's one state variable. And of course, the other state variable is the level of water in the routing reservoir. So again, this is very conceptual. So instead of having a formal routing model, you basically have just a reservoir that creates a delay. So it stores water temporarily to create a little bit of delay so that the water doesn't reach the outlet of the basin immediately. So 2 reservoirs, 2 state variables, and GR4J is strictly a rainfall runoff model. So the inputs that you see here is total precipitation. Well, it's expected to be rain in that context. So let's say rain and evapotranspiration. So that's the 2 inputs to GR4J. So of course, living in Canada, it's not that convenient to only have a rainfall runoff model. We need to have something to account for snow. So it needs to be just a little bit more complicated than that. So there is fortunately a very simple snow accumulation and melt model that was also developed in France in the same team. It's called Semanage. It's a model that takes several inputs. So not all the inputs are actually listed there. So it takes the total precipitation, so not just rain, but really the total precipitation. Mean temperature, the minimum temperature, the maximum temperature, and also some other variables. So for instance, it needs to have the altitude of 5 zones in the watershed and some other information to, for instance, modulate the temperature and the precipitation as a function of this altitude. But basically what it does is that it separates the total precipitation into rain and snow, depending on different temperature threshold. It can also be a mix of rain and snow. This is something that Semanage does. It computes the accumulation of snow, and it also computes a cold content. So this cold content is a state variable of Semanage. It's a value in degrees Celsius. It then computes the potential melt, computes an estimate of the area of the watershed that is covered by snow. That depends on QNBV. So QNBV is another input that needs to be provided to Semanage. So it's basically the mean annual snow that the watershed receives. And it computes melt and the vertical inflow. So the vertical inflows is just rain plus snow melt. So initially, what I wanted to do was to implement this framework. So the figure that you see on the right is the general methodological framework for this data assimilation method with GR4J. So you have the GR4J model there in green. You have your inputs. So in my case, the inputs that I use is the vertical inflows. So this is rain plus snow melt, the potential evapotranspiration, and both in terms of the calibration sub-data set. So this is the inputs to GR4J, which then simulates stream flow. By using the vertical inflows that I have previously computed using Semanage, I'm avoiding the use of snow-related state variables, and I will explain why I want to avoid those variables a little bit later. But yeah, initially I have only 2 state variables, which are the level of waters in the 2 conceptual reservoirs of GR4J. What I want to do with neural networks, so those are 100 neural networks. I want to create an ensemble because I want to have an estimate of the uncertainty on my state variables. So I don't just want one multi-layer perceptrons. I want several of them initialized randomly. And I want them to learn the relationship between the simulated stream flow and the corresponding state variables. So because this is all in the world of GR4J, if you want, this should match pretty well. So the simulated stream flow should match with obviously the state variables that generated it. So I want the neural networks to learn this relationship. However, because the same value of simulated stream flow could originate from different state variables, I want to constrain the relationship a little bit more. And for that reason, I will have additional input variables to the neural networks. So again, I will mention a little bit more about those additional variables later on, but their role is to constrain the situation a little bit more, if you want. So this is also illustrated here. So I have, for instance, more than one time step of simulated stream flow. So time step t, t-1, time -2, t-2, for instance, and maybe the same for some auxiliary additional input variables. And I want to compare the state variables that are simulated by the neural networks with the state variables that were really computed by GR4J, and I update the weights and biases in my multi-layer perceptron in order to get a really good agreement between the simulated state variables and the not observed, but the ones that were simulated by GR4J. So hopefully after that, the relationship between the state variables and the stream flow will be learned. And I should be able to use this ensemble of neural networks to perform data assimilation. So when we move to the other side of the figure, the main thing, but the only thing that changes really is that instead of providing the neural network with simulated stream flow, I use the observed stream flow. So by using the observed stream flow, but the same relationship between stream flow and state variables that was previously learned by the neural networks, hopefully I will obtain new corrected values for the two state variables of GR4J that I will then put back into GR4J in order to obtain a new version of the simulated stream flow after data assimilation. So that's the general framework. So this figure is actually quite important because the entire methodology is there. Okay, so this project I did not do alone. I had colleagues from McGill contributing, and one of their contributions was to suggest that maybe we also try a different type of machine learning technique. This was extreme learning machines. It's actually quite similar in terms of architecture as a multi-layer perceptron. It's just that in that case, there is no iterative training. So this process here of comparing the output of the neural network with the target, if you want, and updating the weights and biases in the hidden layer, it's not existent in the extreme learning machines. So instead, the parameters of the hidden layers are randomly generated, and the parameters for the output layer are computed instead of, so there is no training. And what we wanted to test in this whole project is, the first hypothesis is that the idea of using neural networks for data assimilation would work, and it would work well. And also my colleague from McGill was pretty convinced that extreme learning machines would outperform the multi-layer perceptrons. So we also wanted to compare that, the two techniques. We wanted to use initially 5 catchments, but with this one, the one in Australia, I was much too ambitious, I would say, retrospectively, because this one is basically in a desert. So it's a very, very long series. They have amazing data in Australia because they've been monitoring rivers for quite a long period of time, especially comparing to Canada. It's very impressive. So it's a very long series of zeros. So that's very problematic to train any machine learning technique. So it didn't go well. So we eliminated this one. And it's not only machine learning, it's also a problem for GR4J, because GR4J being so simple, and especially in its representation of soil, it's very difficult to model that type of catchment using GR4J, especially because of the soil process. So in the end, we had one basin in Mexico, one in Canada, of course, one in Belgium, and one in Germany. This one has 2 subbasins, the Main River, but we only used one of those subbasins. And we had pretty long records of data, which is good. So we were able to split each data set into 3 portions. So calibration, validation, and a final test that we kept only for the end. It's not the same dates, though, for all catchments, just because the data availability was different. So the column here is just very, very short abbreviations for the name, Mistasibi. Then this one is Schwerbitz. This is the name of one of the subcatchments of the Main River. This is Urt, and this is Los Idolos. Okay, The input variable selection was also a contribution from McGill. It's a method based on conditional mutual information. And it's a toolbox in MATLAB, again, that's available here at that address. And it basically computes the information content in different pools of candidate input variables in relation to the outputs that we want to model. So I tested a lot of input variables. So of course, stream flow, it's the only one that is absolutely required, but then I had precipitation and temperature and evapotranspiration too, I think, for a very long period, so 1 to 15 days before T0, so that's a lot. And we applied this method of input variable selection separately for each catchment. And so the input variables are not always the same for each watershed. I will show a table of the input variables a little bit later. But first, I want to go back to why I wanted to avoid using snow-related state variables. So this is the graph. The explanation is in the graph that is on the right. So what you see in that graph is an illustration of the problem. So those are the two state variables of Sémanège, so the calorific deficit in degrees Celsius, and the percentage of the basin that is covered with snow, and you have the dates here. So in black, you see the state variables that were really computed by GR4J. And you have many black lines. The only reason for that is because I had several parameter sets for GR4J. So it's just different parameterization of the model, but it's all simulated by the model. And in gray, you have my very first attempt at including the snow-related state variables in this data assimilation framework. And it really did not go well. Okay, and I was a bit discouraged when I saw that, because what you can see basically is that we have, this is for the Mistassini watershed, so there is definitely snow on this catchment, but not in July. Okay, there shouldn't be any snow during the summer, so this here doesn't make any sense. It's not possible, and there is something weird also with the calorific deficit. So basically in the summer, everything should be 0 for the state variables of GR4J. Not GR4J, but Sémanège. So of course you could say, oh, it doesn't matter. You can define dates for summer and just set all those state variables to 0 when it's summer, but it's not very satisfying to do that. So I definitely did not want to do that. And that's why I preferred to simplify the problem a little bit, at least for this first proof of concept, and just remove the snow and use the vertical inflows as inputs instead of using the total precipitation and updating the state variables of Sémanège. So that's why. This is the result of the input variable selection. So you see that, for instance, for Mistassini, what was selected by this information theory toolbox to select the state variables is the stream flow. So Q is always for stream flow. So the stream flow 2 days prior to the assimilation, by up to 2 days before the assimilation, and the temperature up to 5 days before T0. For Schwerbitz, we had more state variable, not state variables, but input variables. So for instance, for stream flow, we go back to 10 days before T0, and Oort 3 days, and so on. And for Los Idolos, we needed precipitation, or rather like vertical inflows, but in that case, it's in Mexico, no snow. So it's really rain. Another thing that we tested, we did lots of tests to figure out the best architecture that we needed for the multi-layer perceptrons. So we tested different numbers of hidden neurons using a maximum value that was computed using this formula that is slightly modified from those authors. So here in this column, you have not the actual final choice for the number of hidden neurons, but just the maximum number of hidden neurons that was tested. So we did not go above 28 for mystacity, for instance. And the training philosophy for the ensembles of neural networks, it comes from this paper that I published a while ago in 2010. So it's basically to look at everything from an ensemble point of view. So we don't want to take the ensemble of neural networks and average everything to have one single deterministic value. We want to keep the whole 100 MLP or ELM ensemble. So in this paper, I basically explained that if you want the ensemble to perform well, it's important that you keep some diversity in your ensemble, and therefore it's important that you do not train until a complete convergence of each member, because if you do that, they will become very, very similar. And if you compute confidence intervals using your ensemble members, those confidence intervals will be too narrow and not representative of the true uncertainty of the situation. So it's basically an early stop training based on ensemble performance criteria. So those performance criteria that are specific to ensembles, the two main ones that we use is the CRPS. The M here is just the mean CRPS. So we want to average that over all the days. And the same for the logarithmic score. So you have the equations here for both scores. So you can see that the CRPS, we compute a difference between the forecast distribution. Here it's for stream flow. It could be for the state variables also at a given time. And we compare that to a Heaviside function. There is a square, and then we compute an area. So this is illustrated here. Okay, so this figure on the right is basically just an illustration of of what the CRPS represents for one given time step. So for this particular time step, I have an ensemble, and from this ensemble, I can fit a probability distribution function. So this is represented in blue. This is the cumulative probability distribution function. And the observation, so for instance, the observed stream flow after data assimilation, will fall somewhere, and it will be a deterministic value. So because we want to compare a probability density function with a deterministic value, we kind of have to disguise the observation into something probabilistic. So that's why we use the Heaviside function. So it will be 0 until the value of the observation, which is here close to 0. And then the probability will be 1 once you reach the observation. And what you do when you compute the CRPS is that you want to compute the area. There is the square. I'm kind of ignoring the square in my figure, but you want to compute the area between the two curves. So that's the gray portion here. And you want this area to be as small as possible, because if this area is small, it means that there is a really good correspondency between your probabilistic forecast and the observation. And if you would have two deterministic objects, it would be nothing different than computing the mean absolute error. So the mean absolute error is actually the deterministic equivalent of the mean CRPS. So this is for one time step, and you do that for all the time steps that you have in your calibration data set, for instance. The logarithmic score is more simple a little bit, but it's also different in nature in the sense that it's a localized score. And what I mean by that is that for the computation of the logarithmic score, we don't look at the entire probability distribution. We only look at the probability density that corresponds to the observation. So here my observation would be 0. again, and I will draw a line here until I reach the probability density that corresponds to my forecast. So the forecast is in blue again. So this time it's not the cumulative probability density, it's just the small f. And I will take the logarithm of that value of the probability density, and that's what will give the logarithmic score. So that's for the evaluation. Now, as I said, we did a bunch of tests to try to figure out the architecture of our neural networks and MLPs. And here you see some results for that for all the 4 watersheds. So in that figure here, the number of training epochs varies. So I went until 200, which was way overboard. I should definitely have stopped before, because you can see that it's almost an asymptote. So I have all those training epochs. I compute the CRPS of the ensemble, so I have 100 members, and I tested different number of hidden neurons. So from only 1 neuron in the hidden layer up until n neuron, and this n neuron value here is what I had in the table that I showed you previously. So this is the maximum. So for instance, for Mistasibi, n, the maximum value is 28. It will be different for each catchment. So after that, we also computed the CRPS looking at different numbers of neurons in the hidden layer, because we want to adjust both the required number of training epochs, but also the architecture of the neural networks in terms of how many hidden neurons we need. So we also plotted the reliability diagram, which is another performance assessment tool. It's specific for reliability. We want to verify that our ensemble are reliable. So for instance, if the ensemble is reliable, and I compute the 95% confidence interval, it is expected that this 95% confidence interval will contain the observation 95% of the time on average. So that's basically what we want to see. So we want to verify that for the 95% confidence interval, but also for a variety of other confidence interval. So for instance, 15%, 20%, and so on. So that's basically what you see on this graph here. You have on the x-axis different nominal values for the confidence interval. So from 0.15, so 15%, up until 95%. And on the y-axis, you have the effective coverage. So what percentage of observations really actually fall into that interval. So if the forecasts are perfectly reliable, everything should fall on this diagonal line that you have here in black, bold, not character, but in black. So as you can see, we did a comparison for different number of hidden neurons, and also for different number of training epochs each time. So for instance, looking at this, it looks like for the Bayes-Schwerbitz, 5 epochs with 8 neurons would provide a good reliability. So 8 neurons is this one. Okay, and 5 epochs is the line in blue. So we can see that the line in blue here basically follows the 95-degree line that we have here that represents perfect reliability. Okay. So this here, looking at all the results that we had for those comparison for the architecture, we were able to conclude that for Mistasibi, we would choose 20 training epochs with 10 hidden neurons. And as I said, for Schwer bits, we had 5 epochs and 8 neurons, and so on. So this is for the multi-layer perceptrons. We did the same for the ELMs. It's just that, as I said before, for those extreme learning machines, there is no training. So that's why there is no number of training epochs required. It's just a number of hidden neurons that needs to be determined. So then, once we had obtained our final architecture and our final choice of models, we could perform the assimilation as such. So that's what you see here. It's an example for the Mistassini catchment. It's for ELM, this one. So I have one for ELM and one for MLP. So you see here the level of water in the production reservoir. So this is the reservoir in GR4J that represents the soil. And the same thing in the routing reservoir. So in blue, it's the state, it's the open loop state. So just the state variables that was computed at every time step by GR4J for the test portion of the database. And the dots in gray are the 100 values for that state variable after data assimilation using the extreme learning machines. Unfortunately, those reservoirs are fictive, so it's not something that obviously exists in real life. It's not something that we can measure. So we can only notice that it's different. So after data assimilation, the state variables are different than before data assimilation, which is kind of expected. But is it better? It's hard to know. So to know if it's better, we have to look at stream flow. And that's what we have on the bottom panel. So in red, you have the observation, again, for the test portion of the database. In dashed black, you have the open loop simulation. And again, in gray, you have 100 values for the simulated stream flow, but after data assimilation. So what we can see, for example, here is that although the simulation was already decent, it was pretty good, even before data assimilation, it's even better after data assimilation. So here we can see that after data assimilation, the simulated stream flow is closer to the observation than when we just had the open loop simulation. And in addition, we have some sort of estimation of the uncertainty. It's not, I would say it's not a complete estimation of the uncertainty in the overall simulation, but at least it's a start. And again, I cannot see anyone. So, and I'm just talking. So if you have questions, you can interrupt me. There's no problem. So this graph on the left-hand side is the same, but for the multi-layer perceptron, it's the same watershed. So Mistassini again, with 20 epochs and 10 hidden neurons, same principle. We see that we have a little bit more uncertainty with those multi-layer perceptrons, and also that we have less extreme values, if you want. So if we go back to the previous figure, we have this strange behavior for larger stream flow that seemed to be overestimated by the extreme learning machines. We don't have that for the multi-layer perceptrons. And we computed also the scores, so logarithmic scores and the CRPS, in a perfect forecast setting. So I have this figure multiple times. I think I will just show, the next ones. So I will show this one. It's the same thing, okay, the figure that you have on the right-hand side. So it's the logarithmic score for all the catchments. So A, for instance, is Mistassini, B is Oort, and then, I'm not sure. I think this one is Los Idolos, and this one would be Schwerbitz. So it's the logarithmic score in a perfect forecast setting. So what I mean by that is we have a context where we assimilate, we perform data assimilation at time t0, and then we kind of let the model run, the GR4J model, we let it go for 10 days, and we provide it with the observed meteorology. So the observed precipitation and evapotranspiration, not precipitation, but vertical inflow and evapotranspiration. And this is to see how the effect of data assimilation will deteriorate with time. So the logarithmic score, we want this to be as small as possible, where it's a measure of error, if you want. So the smallest is the better. And the horizontal line is just to recall the value that we had at T0. So for instance, we can see on figure A for Mr. B that the MLP are the ones that perform best. And we can see that the logarithmic score, the value for the logarithmic score increases gradually between time T0 and 10 days. So it's just that the effect of data assimilation gradually goes away and the state variables get a little bit closer to the uncorrected values. And in those graphs, you also have green lines and curves, and this is for ANKF. So this was a comment from the reviewers in the initial version of the paper. So if I go back to before, where I was here, this is basically the same figure, but without the ENKF. And when we submitted that paper, one of the reviewers said, well, it's all very nice, but how does it compare to a more, let's say, traditional data assimilation method? And he suggested that we do a comparison with a particle filter or an ensemble Kalman filter. So fortunately, there is this toolbox, which at the moment is only in MATLAB, but it's coming into Python. I think there will be a release soon. So Hoopla is a toolbox that contains 20 hydrological models. They are all a bit similar. So it includes GR4J. It's all lumped conceptual models, but it also includes an ensemble Kalman filter framework. And it suggests default parameters based on the literature for the ensemble Kalman filter. So we use those default parameters. And it's very important here when looking at this figure to be conscious that the ensemble Kalman filter here was not fine-tuned. So it's not exactly a fair comparison. And the objective is not to say, oh, our method is so much better than an ensemble Kalman filter. It's just to show that it's at least comparable, because I'm pretty sure that we could fine-tune the parameters of the ensemble Kalman filter and all the distribution of uncertainty around the inputs and the output to make it more performing, but we're at least comparable to the ensemble Kalman filter with our method.
Professor Maria-Amélie?
Yes. Yes.
The ensemble Kalman filter was also implemented in MATLAB?
Yes, so it's in Hoopla, okay? So Hoopla is, it's all in MATLAB. It's a really, really nice tool. And as I said, it contains 20 hydrological models, but also the ensemble Kalman filter and a particle filter. And for both the ensemble Kalman filter and the particle filter, there are default parameters that are suggested. I would say that they are very classic versions. Like for instance, the particle filter, there are almost an infinity of different variants of the particle filter that exist, but this one is very classic. And yeah, it's a very simple application, but at least it's very quick to apply that.
So yeah. you use one already routine for ensemble Kalman filter in the MATLAB.
Yes.
Okay, thanks.
Yes, so it was an addition that we did not plan initially. And yeah, I'm really looking forward to using UPLA again. This is something that I want to mention a little bit later, but at the moment I'm waiting for the Python version because I decided to quit MATLAB entirely. This is also a little bit of a variant of other graphs, is the CRPS. So this was the logarithmic score. This one is the CRPS, and I have another figure with the CRPS for the decomposition. So this one is the decomposed CRPS. So in black, you have the total CRPS. So for instance, A is again Mistassini. You have the potential component and the reliability component. So the potential component, what it represents is the maximum or the best value of the CRPS that could be potentially reached if the forecasts were made completely reliable. And what we see here is that the reliability component in red for this watershed Mistassini, it degrades, is the main thing that degrades. So what it's telling us is that gradually over the course of 10 days after data assimilation, we are losing reliability. But the potential component, it could actually improve because it gets a little bit lower, but it's not flat, but yeah. The main thing is the reliability here. So for this other catchment, we see that the reliability is basically constant throughout the horizon of 10 days, but we have a little bit of variation in terms of the potential CRPS that could be achieved if the forecasts were made to be completely reliable, and so on for the other catchments. It's just further tools to examine the CRPS in greater detail. We also plotted the CRPS with the ensemble Kalman filter. So that's the same principle as before. So for instance, for Mistassini, it's actually interesting, this one. So the CRPS and the logarithmic score, they sometimes disagree. And we have a good example here. So if I go back to the figure with the logarithmic score, just a minute, and for the Mistassini catchment again, in both cases, so for both the logarithmic score and the CRPS, we want a low value. So the smaller is better. And we see here that we have a bad value, if you want, of logarithmic score for INKF compared to the two machine learning techniques for Mistassini. So the green lines are higher. And if we look at the CRPS, it's not really the case initially. So initially, the ensemble Kalman filter seems to be more efficient because it has a lower value of CRPS than the two other methods. But when we move to a longer lead time, it switches, and it seems that the effect of the assimilation with this uncalibrated ensemble Kalman filter degrades faster than the assimilation using the machine learning techniques. And the disagreement between the scores can be explained just because of the fact that they are very different in their natures. So if I go back to the figures of the explanation for the scores, so you have here the figure that I showed for the CRPS to explain the computation of the CRPS. And what we see is that it's really a computation of the area between the two curves. So we are really considering the entire probability distribution function for this one. For the logarithmic score, we are only considering one value, which is the probability density that is associated to the observation. So what happens here is that when the observation falls completely outside of the ensemble, we have a problem. Basically, it penalizes very, very heavily that type of situation. So when you have a streamflow observation that is very far away from the forecasted distribution, it's very bad according to this score, whereas for the CRPS, it's bad, but it's not as bad. And another thing with the logarithmic score is that you can have to compute the logarithm of 0, and it's a problem because then you end up with an infinite value for the score. So when that happens, you have to replace the 0 with a very, very small value, and this is a little bit arbitrary in that case. So I think that it's one of the reasons why many people prefer the CRPS to the logarithmic score. But personally, I like both. I just think that they're different and they provide different information. So what I presented here today is published since 2020. So it's a paper in water resources research. And as I said at the beginning, I've only recently started working on this again in a kind of a second phase. And the first phase was to really move everything to Python. And I did that with an undergrad student. It's still ongoing. Oh yeah, and I forgot to mention that. Sorry, I'm moving a topic a little bit. So just to go back to the hypothesis, the first one is verified for JR4J and for the given catchment. So it's kind of it remains a limited experiment. The first hypothesis was that this whole framework would actually work and that it would be possible to perform data assimilation using machine learning techniques. So it works for our setup. But now, of course, we would like to perform tests on other hydrological models, maybe perhaps even distributed models and physics-based models. We would also like to have more catchment. And the goal of that is to gradually try to generalize that technique to a whole variety of situations. The second hypothesis was not verified. So we found that multi-layer perceptrons outperform the extreme learning machines. So a bit of a disappointment for my colleague at McGill. But again, we could eventually test other types of neural networks or even other machine learning techniques. So there are lots of possibilities. And we want to include snow-related state variables again. And that's actually the first thing that we want to do because it's very inconvenient to have to find a sort of trick to avoid the problems with snow-related state variables. So now we're at a point where we want to face the problem instead of avoiding it. So that's basically what we're working on right now. The translation, as I said, is ongoing, but it's pretty advanced. And we are using this package for JR4J and Semanage. It's available on GitHub. We would like eventually to quit this package and switch to Hoopla. Hoopla is there, so it's on GitHub, but you will find it here in MATLAB. The reason why we want to switch eventually from RRMPG to Hoopla is just to have access to those 20 models. It's, as I said, similar models, but they're not exactly the same. So it would already be a good step for generalizing the technique. So instead of having just JR4J, we would have this lumped version of HBV, for instance, that is in Hoopla. And in terms of snow, sorry about that. In terms of snow, what we want to do, and this is also a short-term thing, we want to try to move to more theory-guided machine learning. So with another student, Vincent, we recently published a review about theory-guided machine learning for completely something else. Vincent is in hydrogeology, and he models the recharge of groundwater, but using a more theory-guided approach. So we want to use that to try to solve our problems with snow. So basically, the idea is to use the CCI snow cover information, which is available here, to try to constrain the training and basically add another term in our objective function, another mean square error between the snow cover that is computed from the assimilation during the training, with what is observed and available in the CCI dataset. Because here we can have direct observation. It's a satellite observation of snow cover. So we could try to penalize the neural networks when they issue unrealistic values for the snow cover during the training. So I hope that with that, we would be able to have neural networks that are better at representing the relationship between state variables and stream flow, but also snow. So that's all part of the current work that is ongoing. Yeah, so this is not super important, but it's just the new modified framework. So now adding back the 2 additional state variables that come from Semanage, and having a more complex objective function that would be comparing the state variables of Semanage with the observations that we have from CCI. So I'm not sure how I did in terms of time. So I will, this is not really what I want to do.
Well, we have a half hour.
Oh, okay. I was so quick. Okay. Sorry about that.
And so, but by the way, we have some questions in the chat. And so
okay, that's perfect. Yeah, so I can
right.
I can answer the questions. I'm sorry, maybe I spoke too fast. I hope it was clear.
No, that's okay.
So
there is some question here. It's from Claire Mahi Amel. Could you say a little bit more about the extreme learning machines, please? If they are not trained, how are this neural network can be computed the weight parameter set in backpropagation performance 1? Thanks.
Yes. So I see actually both questions at the moment. So there is also another question about the layers. So I will share my screen again. It will be easier for the first question, I think. Okay, so and I will put that back.
And the second question is...
So yes, I will go back to the appropriate slide. There, okay. So there's no backpropagation involved for extreme learning machines. So it's really just those equations. So for the hidden layers, the parameters, it's very easy because they're just generated randomly. So you do that and you don't have to preoccupy about those if you want. It's for the output layer weights that it's a little bit more complicated. So we just use that equation here. So it involves the output of the hidden layer and the target variable. So those here, the G here would be the output of the hidden layers, and this is the target variable. And this here is the Moore-Penrose inverse. Okay, so honestly, those equations here. It was already in the toolbox developed by John, my colleague from McGill. So I don't know the very deep details about that. So especially, to be honest, the Moore-Penrose inverse, I did not code that portion myself. It was John's contribution. And yeah, as I said, T is the one of the target variable. And this one, yeah, this one was actually, I said it's the hidden layer output, but it's more complicated than that. It's what's developed here. So it's a sigmoid function. So it's really what you have to, I think, keep from that, if you want, is that for the extreme learning machines, we generate the hidden parameters, the parameters of the hidden layers that are generated randomly. And for the output layer weights, they're just computed using that hidden layer and the target variables, and there is no backpropagation for this. But in the second phase of the study, so what we are working on right now.
Sorry.
Yes?
Hidden layer parameters means the weights, connection weights.
Yes, it's the weights here.
Yeah, it's not the number of neurons or something.
No. So actually, the output layer, we always have the same number of outputs. So it was in the figure here. Okay, so our outputs are the two state variables of the GR4J model. So the two levels and the two reservoirs. And the input variables, they were also defined in another way using the information theory toolbox that I mentioned earlier. So like the basic idea, so in terms of input and outputs, it's the same for both MLPs and extreme learning machine. What will change though is the number of hidden neurons. So I had a table a little bit later about that in the results. Yeah, so here it's our final selection for both the MLPs and the ELMs. And you can see that we don't have the same number of hidden neurons for the MLPs and the ELM for any catchment. So I don't know if it's much clearer. I hope so. But yeah, we decided after that study to not continue with the extreme learning machines. So at the moment, we're just using multi-layer perceptrons because they provided better results. But it could be interesting to test completely different types of neural networks, including perhaps the LSTM network, because it could be it could potentially be useful in the context where we have that here. Okay, so for instance, for Schwerbitz, we have used the stream flow up to 10 days prior. So we could have a completely different approach if there could be some notion of time, if you want, in the machine learning technique itself. It would be quite a big change, I think, but maybe that's also something to consider eventually. So I hope it answers the first question. I saw also that there was another question in the chat about trying to see if it would be interesting to have more hidden layers. Why not? We could do that. At the moment, we're really trying to have a toolbox, like a basic toolbox in Python that's very clear and that we would be comfortable distributing. Because at the moment, everything is on GitHub, but it's a private repository on which I just work with my students. But eventually, we would like to make this publicly available, and we would like to test a variety of other things. We could include testing the number of hidden layers, but it could also be, I mean, someone else testing that. I think there are many possibilities to improve that framework further. So yeah, that's a good suggestion. I don't know if there are other. Oh yeah, okay. Okay, so another question, a comment. There is Octave software. Yes, I'm aware about Octave, but I just think that Python is a pretty good choice because it's well known. And because it's well known, there are lots of packages that already exist that I can reuse. I'm not particularly a fan of coding everything from scratch. I think that's also one of the reasons why I'm not I really don't want to be an early adopter of Julia, for instance. A lot of people are talking about Julia, but I think that it's way too early for me. I want to use a language where there is a very big community and a lot of packages already exist. So I don't really want to use a MATLAB lookalike, if you want. I prefer to just use Python. Another comment was for the MLP neural network, why are so few epochs for training? Okay, that's a very important question, and that's related to the paper from 2010 that I mentioned. This is exactly what we do in that paper. We demonstrate that if you want to have a good ensemble, you are not looking at exactly the same features, if you want, than if you want to have a really good deterministic situation. So we want the ensemble to be good and not necessarily any individual members. So the CRPS, for instance, it will look at the entire distribution, and if the distribution is very narrow, if all ensemble members are very, very similar, it will penalize the CRPS and the logarithmic score, even more the logarithmic score, very, very heavily. And I think we see that a little bit on one of the figures that I show. So I will share my screen once again. Okay, but I lost the presentation. Oh, one moment. Okay, it's there. So the paper that I'm talking about is this one. Okay, so an experiment on the evolution of an ensemble of neural networks for streamflow forecasting. So there is no data assimilation there. It's just streamflow forecasting using neural networks, but it's kind of the same principle for ensemble consideration. And here you see that I computed the CRPS. So the CRPS uses the whole ensemble, so all 100 ensemble members. And I computed that for a bunch of epochs. And as I said, I went until 200 epochs, which is way too much, because we want the CRPS to be low. Okay, a low value of CRPS is good. So what you can see is that it drops very, very rapidly during the very first epochs of training. And after that, of course, yeah, it gets a little bit better, but it's very marginal. So what we really want is that big improvement of the CRPS that we get here at the beginning. So we really don't need to train for a very long time for the ensemble to be good. So it's like we're not training each individual multi-layer perceptron up to perfection, if you want, because we want this diversity in the ensemble. So that's why.
So the paper from the 2010 is the forecasting
yes.
Using ensemble
yes.
by neural networks. But
yes.
the focus is forecasting. Okay.
Yes. Yes, but it's the same training philosophy. So you can apply the same, the same philosophy when you want the neural networks to learn how to assimilate the state variables, because we still want to have this diversity in the state variables, because the state variables, they are also uncertain, especially since they are things that don't exist in real life, right? So this reservoir here, the production reservoir, I cannot measure it. It's a completely imaginary reservoir. So of course I want to have the best possible estimate, but there is definitely an uncertainty on that estimation. So I want to have that uncertainty and represent it with my ensemble and with my neural networks. So I cannot see the comments at the same time, so I again have to stop the sharing. Did you analyze autocorrelation to decide how many time steps in the past to use? Yeah, this is also related to the to the input variable selection. No, we did not do that, but I think it's kind of de facto included within the information theory toolbox. But I also have to say that we are now looking and thinking about a different method for input variable selection, because I don't really like it. I would like to have something more simple and also something that could be more easily automated. What I mean by that is that I would first like to be able to take any catchment with some basic characteristics very easily available, and maybe compute an estimation of the response time of the catchment, for instance, and start my selection of the input variables from that. But then that's basically the point where I am for input variable selection. I still have to think about that, but this is also something that I want to change. So if you have suggestions, ideally, I would say I would like simple suggestions, but simple but nice. So yeah, this is a component that we want to change. And for different rivers, is the same neural network architecture used? Not really. So for all rivers, we only have one layer. Okay, so only one hidden layer for all our rivers, but with different number of hidden neurons in that layer. So there is a part of the architecture that is the same. The outputs are the same, one hidden layer, but what's different is the input layer is different. We don't have exactly the same inputs for different rivers, and we also don't have the same number of hidden neurons. They were kind of calibrated. As I said, we tried a bunch of things to see what combination was the best for each river. Now, I don't know if there are other questions.
Well, if you want to add some one additional comments, or
I don't really have additional comments at the moment. No, as I said, I would really have liked to be able to do a sort of demonstration with the new version of the codes, but it would be, I mean, I like to live dangerously sometimes, but this is too dangerous. It would be, it would not go well. So okay. Yeah, I will not do that.
Well, anyway, I think that Python is a good idea to migrate all of your code for this. And the Julia, related to Python and Julia, I think that I only know that Julia has one this atmospheric dynamic model implemented on Julia. I don't know if there is someone similar thing using Python.
Okay.
But I think that Python, there is much more libraries and something that you can use it's available on the internet.
Yeah.
And so
I think so too. It's just that
maybe it's a better idea.
It's just that there is constantly something new, right? And I have my students. I have one student in particular who is very keen on trying very, very new things. And he's like, you should look into Julia. And I was like, no, I don't think so. You look if you want, but not now. But I mean, it's possible that maybe it will become like the prevalent language one day. I don't know, but for now it's a bit early for me.
Okay, Professor Professeur Marie-Amel, merci beaucoup pour votre présentation.
Ah, merci, très bon français, merci.
Non, ce n'est pas vrai. J'ai oublié beaucoup de paroles d'expression en français. Aujourd'hui, la communication en français est très difficile pour moi.
Ah, ok, mais c'est quand même très bien, c'est très bien. Merci beaucoup.
Thank you. Thanks a lot for accepting our invitation, and very amazing talk. It's a little bit different from we have one presentation yesterday introducing neural network, but emulating another method for data assimilation, just for saving CPU time. And so this is one thing that I would like to see in your future works. The CPU time after that you get in your Python programming, the CPU time between ensemble common filter and neural network.
Yes. Okay. Yeah. Very good. Very good suggestion. I will look into that. Thank you, and thank you for the invitation. It was really nice.
Okay. Thank you again.
Okay. Thank you.
We were very happy that you have attended us. Thank you very much. Okay, we are go back to let me see, in 1 hour. It's we are here.
It's 5 o'clock.